Is everybody ready for the last official event of the conference? Yeah. Can you still pay attention? Yes, great. Because now I can present Jens, who will tell us what's new in Snap 11. I wanted to prepare a speech about Jens, but I forgot and didn't have time. So I'll just hand over to Jens. I'm really glad working with you, and I'm really looking forward to hear again what's new in Snap 11 and be presented by you. So thanks.
Oh, thank you, Jekka. Hey, you all know me anyway. Welcome to What's New in Snap 11. There actually isn't all that much new in Snap 11. I've made a long list, and you can read it up. It's mostly little stuff underneath the hood. The part that I've already kind of said so earlier today has kept us, Jekka, me, and Uwe, up like for a long time was how to do AI in Snap. We've been doing this before. So here's what's new in Snap. I've got something to say about data, about new extensions, and about neural networks. So as Bernat has found out, we have this maxim when we're developing Snap. It's obsession-driven development. And that precisely means somebody Googles something and finds something they don't understand. They say, wow, I found this thing. It does magical things, and it's apparently math. I don't understand the least of it. And then we go and we read the Wikipedia article, and we understand even less. Then we ask math teachers and Berkeley professors about it, and they don't know, or we don't understand what they say. Then we watch YouTube videos, and years after, we find out wacky ways how to do stuff. And so we've decided to write some of these wacky things down. This has been a project for, Bernard got a head start, but for the rest of us, we started this year. And one thing that, like we were already well into the book, when Bernard asked me to add something to Snap because he needed it to explain this thing he was working on in this book we were writing. And I was like, nah, why should I add that? And then, yeah, sure, add it because it's just neat. So what I need is just this one thing. I need a block that gives me a color. So when I click on it, it gives me a color. And so I can put these things into other blocks and into lists and stuff like this. So this is the first thing that's new with regards to data. We now have first-class colors in Snap. And I'm not terribly excited about first-class colors at first, until I got to play with them a little bit. So one thing when we talk about algorithms, which is the name of our book, algorithms, one fun algorithm that keeps coming up is, thinking about algorithms themselves, thinking about what it entails to be a process, like we're supposed to be the science of process. So one process is how to, go from A to B, how to transition from one state to another state. And a cool way is, let's just build a block around this. So I want to make a transition block. It's an operation. I'm going to transition from start to end in n steps. And so what I want to do is I can formulate this. Start is going to be an input, as is end, as is the number of steps. So what I can do is so I've already got this. So for example, I'd like to transition from 3 to 7 in 4 steps. And I want to get the numbers to get there. Now it doesn't do anything, so I need to do the math. So the math is probably, I'm going to get the difference between the end and the start. I'm going to divide it by the number of steps. Now I've sort of got one step. Then I can do the start plus this times whichever step I'm at. And now I hope I can use map for this with the numbers from 1 to the number of steps, but I also want to get kind of the first thing where I start at. So this should give me something that I can work on, work with. Let's try this. Let's give this a try. So yeah, I get the numbers. That's how computer science usually works, right? We write a function, kids, this is great. You can do some stupid math stuff. You can also do other numbers, whatever. The cool thing about Snap that we've told you all along, and it's been a theme of this conference, is that, you know, if it takes one number, it takes one number in any dimension, or it takes any dimension of numbers. So, for example, if, you know, put Alonso here, Alonso has a position. A position is two numbers. It's the x and y coordinate. And, you know, my mouse also has a position. It also has a mouse. What if I want to transition Alonso from its position to the mouse position in, say, 100 steps? And so I want to do this for each item. Let's just keep it item. For each item in here, you know, let Alonso go to that item. And since I'm going to use the mouse position, I'm going to use the keyboard. So as I'm clicking this, Alonso is actually moving. So it's working for one number, but it's also working for a bunch of numbers. Or, for example, one thing that somebody has said, so if we take the Unicode of A, you know, we get a number. If we get the Unicode from Java, not JSON, from Java, we get a list of numbers. If I would like to transition from Java to, let's find a programming language that has 4 letters. To maybe Snap in, let's do this real quick in 7 steps, right? Yeah, I get a table of numbers. That's interesting. I can round these and again put them, convert them back to letters. So now what I get is the steps that it just takes 7 steps to transition from Java to Snap. So this is promising. Another thing that's kind of promising, and that kind of first blew my mind, like, what if I, you know, make a variable? Let's say variables need to be named very explicitly, so I always name them A and B. So I'm going to set B to a new sketch. What if I make a new sketch? Let's say I make a house. So I draw a house. Yay. So I can look at the sketch. The sketch is just a bunch of, like a list of lists of numbers. Okay, so where there is one, actually, I want to get the pen size a little bigger. Let's make another variable, variable A. Maybe I should have done that first. Let's also assign that to something. So let's draw a clef. So now I've got A and B. Hey, what happens if I transition from A to B in 150 steps? Wow, I get some kind of very funky data structure. It's a list of tables. Okay, that sounds interesting. What if for each item in that list, I want to draw that item, I want to draw that sketch? Hey, okay, check this out. Isn't that just, you know, so this, friends, is the gospel of computer science. It's not, you know, doing the math for, you know, how to go from 3 to 7. It's not the formula. It's the same formula. This is a process description, an abstract description of how to go from one point to another from one position. And it is abstract because we can think about it as something that we can apply to many domains. This is not about ones and zeros. This is not about how a processor works. This is not about how technology works. This has nothing to do with technology. This is all about philosophy. This is all about how we humans think about things. And so, see, when Bernard insisted on numbers, see, so we can get things from numbers. So we can get the hue of a color. We can get the RGBA values of a number. So what if we, transition from, yellow to, let's say, dark blue in 12 steps. What we get is another table of numbers, which we can, once we're in numbers, we can do any media with them. We convert them back. We're getting a gradient of colors. Isn't that just also beautiful? We can apply to any medium. Since media is digital, having a computer and thinking about things in one dimension makes it work for any dimensionality. And that kind of abstraction is liberating. It's not something that ropes us in. Okay, one last thing. What if I've got a costume? Like, for example, I've got the costume, like a penguin costume. I now can get, since we have first-class colors, I can get the colors of this penguin costume. And look at this. So now I can see the pixels as colors of the penguin. And of course, because of hyperblocks, we can get, the RGBA of the colors of the penguin, right? And we could try to transition those to the colors of Alonso in, let's say, 20 steps. So we again got a very complicated thing, which we can now turn back into colors and turn back into a costume. Since it's all numbers, look at this. What we're getting is a morph from one picture to another because it's doing it for every dimension in every pixel of this thing. So this is really, when you think about dimensions, usually when we say, oh, dimensions, this is something philosophers talk about, I don't even get it. It's just another list of stuff in there. It's actually something that isn't mind-blowing. That isn't the part of science fiction. It's just very natural. It's very human. It's more difficult to write the vocabulary than to just think about it. Okay, so see, this is why we're writing this book about, because we are always seeing insertion sword or merge sword or bubble sword when teachers and curriculum makers talk about algorithms. And we want to show liberating things, not things that box you in. Okay, so I've just shown you. And the question was really, yeah, but now we've got AI, and we've sort of been wiggling around this AI thing, kind of showing you stuff that is AI or used to be AI in the 60s. But now, of course, everybody knows it's about neural networks. And we've been really struggling hard about neural networks. We've heard all our introductory teasers, so let's just cut straight to the point. When Yadka and I first met to talk about the issue of neural networks, after she'd gotten me to promise to get it done in half a year, which was 2 years ago, we decided that what we want to do is we don't want to use AI to make it programmable, like the magic machine that Dan said, but we really want to show how we can get the algorithms that make neural networks such that we can either teach them or maybe even understand them, or just use them. So if you're not wondering how to teach backpropagation in 2025, you're probably going to all these webinars about let's prompt AI for middle school or let's prompt AI for innovation. I think we as computer science educators need to teach about the algorithm that is behind all of this. But we also want to take a little bit of this wonder away, because it's neural networks and everybody goes like, a neural network. And then there's this picture of a robot and maybe a human brain attached to somewhere. It's this humongous thing that, does things. I mean, it can't be such a big thing because it's nearly ubiquitous nowadays. Maybe we can sort of get it back into proportion where it belongs. And maybe we can abstract it completely away because we're a blocks-based language. And this is kind of the newest idea. And we just got this like barely a week ago. And we're going to show you all of this. Okay, where am I? Yeah, let me show you in Snap. Is that okay? Good. Let me show you in Snap. Okay, I'm going to open a project that we started with. We started with something that we wanted to explain. So here is the example I like. Christiane hates it, and you're all going to hate it for the right reasons. But I like it because it tells the truth. Here is a data set that people are using. It's sonar data. It's sonar pings. It's a data set of a bunch of numbers. This is a sonar pinging to detect sea mines. And now there is an echo, as you all know. And sometimes you find a mine, sometimes you find something else, like a whale or a rock or something. And so this is in the form of a truth table, which means it's got kind of 60 features. And the last column is, either nothing, it's zero, so this means it's probably just a rock, or it's a one, and which is an example for a mine. So let's actually look at this. Since it's sonar data, we can plot the bars. Since all the numbers are between 0 and 1, we probably just want to increase them a little bit. And I'd like to center it. I need to get a specific item. Let's get a random item. Let's look at this. The random item of sonar. Now here's a random sonar signal. You can see the last spot doesn't have anything, so we know this is a rock. This is not a mine. This is a rock. Let's try another one. This is another rock. Another rock. Another rock. Oh, this is a mine. A rock, a mine. When I go through these, and I spend a lot of time going through these, eyeballing them, sometimes when you eyeball data, you kind of see patterns. I think, oh, maybe it's these two protrusions here, or maybe one's more jaggy than the other, or the amplitude isn't as big. I cannot make anything out of this. Also, if you look at this data, it doesn't say anything about what these columns mean. It might just be the signal. We have no idea what this means. And folks, when we think about AI, usually when we teach it with all these well-designed examples of, the iris flower set, and where we have, this is the size of the stem, this is the size of the petal, and we try to reason about this in our heads, and so we can check whether the AI is doing the right thing, and then we trust it to do it for 2,000 features. Here's a data set we don't know anything about, and it tells the truth because this is how this whole neural network craze got started. They were funded by the military doing exactly that, finding out, hey, friend or foe, am I going to kill this guy or not? Okay, so let's start with, when we started building this, we decided, let's do one sprite. I'm calling it Frank, because Frank Rosenblatt, one sprite that does all that. And you might have seen all the examples of how to do neural networks and perceptrons in blocks. And what you always see is this thing where set input 1 to this number, set input 2 to that number, change weight 1 by input 1 times delta. And we've gone through this, like I've spent a year going through shit like this until I found On LinkedIn, of all places, a blog post by somebody who said, oh, I was trying to do neural networks kind of the classical way back in the 90s in a class given by Jan LeCun, who said, oh, if you're using loops and variables, you're doing it wrong because you never find the light. You have to think about it as vectors and matrices. And this is when it dawned upon me, wait, we have that in Snap. We were like the born language to talk about this. So this is what we got on our first day at SAP when Yatka and I, when we were thinking about this is what we came up with. So we want to do a sprite. Like, what if a perceptron, what if a neural network is just a sprite? And we got this to work. This totally works. I'm not going to show you, but it does work. What I spent the next 1.5 years on is getting this to work with multiple layers, with all the examples that don't work. What I came up with the help of Uwe and others, is this thing that I'm going to call perceptron. And see, the change from this, and you've all written more complicated stuff than this. And the kids in your classes have written more complicated projects than this. This is a perceptron. And this is a layer in a neural network. There isn't all that much difference. And in another talk, I can show you exactly what are the differences. We're just giving you the perceptron sprite. This is, and I'm going to show you how we're giving this to you. Everybody has it in their Snap already. It's part of Snap now. And so we have a perceptron sprite, and you see something new. Like you see something that it has 3 messages that it reacts to. Like you can set it up, you can let it predict something, and you can let it learn. But you see, the new thing is that there is a report block underneath this predict hat block. So report is just like it gives something back. So you can broadcast something and wait for the answer. And we've made this so you don't have to make a new block, which you never see in action, but you have to open. But we want this to be a sprite that you can see each script that it does, like a physical plane in an apparatus. Okay, so let's actually try to get this to learn. So what I want to know is I want to get for each sample in my sonar data set, and I'm actually going to shuffle this so that not all the zeros are in one at the beginning. What I want to do is, I want to find out how well this thing works. Let's set up this perceptron. I'm setting up this perceptron. I'm just going to use this. A broadcast setup. When I broadcast setup, I can specify a shape. And I'm broadcasting it to the perceptron. And I'm broadcasting it a shape of how many things go in and how many things go out. Now, I want 60 features to go in because that's the length of my list. And I want one decision to come out. Is it a mine or is it a rock? Okay, so I'm broadcasting this. So now I can actually, what it did is it initialized its weights. I can look at the weights of the perceptron. So I've got a table where the first list is just 60 random numbers between -1 and +1. So now I want to predict it. So for each for each record in this data set, I can say, okay, let me get I know the answer because this is the last column. So I'm getting the target is the last item in that sample. Now I want the perceptron to actually predict it, which is going to be the output. I'm going to set the output to, and now what I can do is I can just request predict from my perceptron, and I can send along the data that I want to predict, right? So this is now the outcome. What it does is it does some matrix multiplication, basically pretty simple. That's for another talk. So now I want to see how this is different from what I'm expecting. And we call this a delta. So we set the delta to the difference from what I'm expecting and what I'm getting. Oh, and I want to count the errors. I want to see how well I'm doing. So at first, I'm going to start the errors are nothing. And now I'm going to change the errors, not by the delta, because the delta can be minus or plus, so they might cancel out, and we might think we're doing fine, but in fact we're just going in the wrong direction. So we're taking the absolute value of the delta, and the delta can be a list because there can be more outputs than one. So we're just adding them all up together. We're just doing the sum of that. And then we want to know how well we're doing. And we're going to not say hello. We're going to say the ratio of the errors with the size of the data set, the length of my sonar data set. And we don't want to know the errors. We don't know success. So we're going to kind of put this around. So this is our success rate. Okay, let's try this. Oh, wait, it's perfect. That's not accepted. That's probably not right.
Should you set data, not delta?
Thank you. My glasses. This is why I need. Thank you so much. Okay. Oh gosh, it's my glasses. Folks, I'm getting old. Somebody younger has got to do this. Okay, so I'm. Okay, so we're about 50-50 chance. Let's get a new set, like another set of weights. Yeah, 45%. Okay, 42%, kind of around 50%-ish, right? It's like a yay or nay.
We just started going and have a bar plot as it goes.
I'm giving the talk. I've got this covered, okay? So now what we want to do is we want this thing to learn. So what we could do is we can broadcast learn to the perceptron, and it should learn from the delta. So when it learns, it adjusts its weights. So now I'm giving a new set. And look at this. Even the first thing, we were around 50. Now let's do another iteration. 59, 62. Whenever you click on this, the AI folks call this an epoch. This is an epoch. So we can see how it learns from its mistakes, how it adjusts. And you can see this. You can see the actual weights change in the same watcher. So this is an important maxim we thought about, because if you look at what this is doing, it's changing the weights by. Now you're used to changing a single number by a delta, but we want to change a whole data structure while keeping its identity. And we can argue about whether, anthropomorphism is helpful for understanding AI. But I mean, the model is that we're adjusting weights without making a new brain every time. So it's actually kind of the model of trying not to have assignment, but instead have an evolutionary learning process. And we felt this is something important because then we can also watch what happens. And now we can do the thing that we can say, we want to actually see how it learns. So I can make a log. I'm initializing that log with an empty list. And every time I'm through with my errors, I'm adding the errors to that log. And I want to find the bars of that log, right? That's what you want to do, like not the neural model, but plot the bars. Plot the log. We probably also need to scale this a bit. So let's try this again. And we need to do this forever, right? Yeah, let's do this forever. And now we can see how this tiny neural network, this perceptron, learns. And we can see it's pretty good. Like it goes like from 50-50 to 75%, like in almost no time. And it's still making some progress, but it seems to be fizzling out at around 80% from what it learns. And, you can see two things about this. This is pretty darn amazing. We don't know anything about what these numbers mean. They might, neither does this thing know anything about it, but somehow training this just on deltas makes it converge on something, like it learns something. Now it doesn't learn as much anymore, but it learns something. And it's actually pretty good, like from 50-50 to like 80%. That's pretty great. But think about 80%. I mean, this is like a decision, friend or foe. Are you going to kill somebody with an 80% chance? Probably not. Are you going to take life and death decisions on an 80% chance? Probably not. It's got to get better than that. And when we're talking about it's got to get better than that, everybody knows, everybody's talking about the XOR problem and the AND problem. That is not helpful because those are kind of mathematical computer science kind of logic expressions that we think they're a problem. Just, you can see it doesn't get much better than that, and that's not good enough. And so the thing that all these books that have been written about this is, what one perceptron cannot do, two perceptrons can do. That's really the thing. So we want you to think about, here's this one perceptron. What if I just make another one? I just clone it. Like this whole thing, I'm not calling it perceptron 2. Hey, now I'm calling it hidden layer. Okay. It is just a perceptron. It's literally just that. I'm not changing anything about this. Oh yeah, let me actually show its weights. So now it's got the same weights because I've basically cloned it. But now what I want to do is I want to also initialize that. So I'm setting up my hidden layer with, let's say it's got these 60 inputs. Let's say it should have 5 outputs. And then I want these 5 outputs to go into my output perceptron. And I want to have one decision that comes out of this. Okay, let's do this. So now I can see the weights of my hidden layer and of my perceptron. Okay, so now what do I need to change? No, I want this whole thing to learn. So my output is going to be a request from the perceptron, but before this, I'm going to request it to the hidden layer. Hey, and I learned something today from Fritz, who just had to leave. We can turn this into a pipe. So I'm piping my sample into a request predict from my hidden layer. And what I'm getting back is I'm piping through the perceptron, which is now my output layer. Now I'm getting a decision back that's gone through both layers, okay? And here's the clue. When we want to learn, now we go back to the perceptron and it learns something and we give it a delta. But we cannot give the same delta to the one before because we don't know what it was expecting. And what it was expecting isn't clear. And this is what they were computing on for, I think, 10 or a dozen years. And it's this line of code. This thing here, that is the current Nobel Prize of Physics. And I've seen more complicated code than that. The mathematicians among you will tell you that, yeah, this is actually more clever than it looks like, because if you take the sigmoid activation function, this happens to be the partial derivative. Forget, it's just this function. They wrote it in their paper. So this is the Nobel Prize, Physics Nobel Prize. Great. I want mine. Okay. So the learn function is also answering kind of the next delta for the next layer. So we also need to turn this into not a broadcast, but into another pipe. Look at this. So what we're doing is we're piping the delta, and we're requesting learn from the perceptron. And what we're getting back from the perceptron is the new delta that we're giving to the hidden layer. So what you can see here is two pipes. One that's going forward to the hidden layer, to the output layer, and one that's going backward to the perceptron and to the hidden layer. One is called forward feeding, the other is called back propagation. Okay, let's try this. So you can see how all these numbers change as it's learning. We can see it's going down. Okay, we've been there before. It seems to stall at 80%, but it's actually confidently going farther. And that's the promise of deep neural network. A deep neural network is something that has more than one layer. We can have as many layers as we want. We can have more clones of that perceptron and just put more steps into our pipe, and we can have as deep networks as we would like to have. And we can see we're already above 90% what it learns. And that is actually quite amazing. It also means that when we look at what's actually happening here, we as humans have no clue. As soon as we have one hidden layer, there is no way we can reason about what's actually going on about this anymore. So all the attempts to, let's just start with 2 features or with 3 features, or if any company, if any mogul is telling you that we're working on explainable AI, they are lying to you. They're working on some chatbot that is going to come up with some gibberish that is going to be an explanation, but it's not going to be what's actually going on. There is no way to explain what's going on as soon as you have one hidden layer. Okay, so this is kind of the long story. This is how we would like to see it. It's almost like it's rapidly approaching a certainty where we can see why military gets excited about this, right? And why bankers get excited about this with just a hidden layer. So we wanted to have something, to create something that is kind of physical enough that you can experience it, that you have actual objects that you can tinker with, that you can clone with, that you have things that you can follow along. And for, high school or university level, we actually think that you have to teach this formula. It's not that hard, and what's going on here. And that you should not use it by having named variables, input 1, weight 32, because that doesn't clear up anything. That just tells you that there's a bunch of data that you need to be very careful about how to pair it. Once we had this, we thought we're done. This is great. Now we can teach neural networks in Snap. We just give everybody this perceptron sprite and tell them about it. And then we thought, well, what about the second goal? The second goal was just what if the neural network and the perceptron were just something that we could use like a sound or like a costume, like not even like a sprite. And so we came up with this idea to turn it into a library. Now, technically, this was a little bit difficult because we didn't have data objects yet in Snap. So I had to build these in. And we released these before. We released these sometime, I think, in October. And let me actually show you first would I want to do this? Because one other thing that bothers us is that when you talk about AI, usually what you do is you download some data set, like the Minds data set, like the diabetic data, like, is it a good wine or not? Is it a forged banknote? That's pretty boring because it's just data. So you split it up, you see a curve that's going down. You say, "Well, a curve is going down. That's so cool." That's actually not very cool. It'd be way cooler if we could use our own data. So let me use my own data. My own data, as you know, is let me actually. Need to play this once is to slow me down, I guess. So, okay, so this is the sound that is my harmonica. And I'm going to try real hard to do this one. Practiced long and hard for this. It's been every German kid had to learn the recorder before learning a real instrument in my time. And this is the hard one where you actually have the wrong way to. Okay, never mind. Okay, so this is my recorder. So I have these sounds like the harmonica, and it's a lot of data. It starts with zeros, but then it's a lot of data. It's too much data, and so I don't want to have a neural net with 200,000 features. So I want to cut it up. I'm going to reshape these samples to chunks of 100. So now I'm chunking them to 100. And now I want to tag these. So I'm mapping these, and I'm appending a marker, like a 0, because it's a harmonica. So now if I look at this, all of these have a 0 at the end, okay? Let's actually do the same thing for the recorder. But the recorder is going to be the 1. Okay, so I'm going to stick these all together into one big data set. I'm going to shuffle them because it's still way too much data. And I'm just going to pick a subset of those. I'm going to pick the subset of, let's pick maybe 400 of those, 500. That's 500. Okay, that seems like a reasonable thing to do. Let's assign those to my data. Okay, now I've got data. Now what we did is we added a library. That's a new library in Snap 11, the neural networks library. That's the one thing that we just want to use neural nets as if they were, just another resource. And the neural networks library has something that you can make a new neural network, and you can specify its topology. So I can make a variable, and I'm going to call this AI. I'm going to say, the AI. Oh, well, actually, let's look at this. Let the AI be a neural network that has, the first layer has 100 inputs because that's what I cut it up, and I want one decision, like is it my recorder or not? So I've got, here's an object, and so what I got is more blocks. What I can do, I can now train my network on the data. And when I train it, what I'm getting back is an error. So I can do the same thing again. I can make another variable. Actually, I don't make a variable. Let's do it just like this. Again, do the variable log. Initialize it to an empty list. Now I'm forever training this and adding the output of that training cycle to my log. And I'm forever plotting the bars of the log. I probably need to somehow scale them. I forgot which one is the right scaling thing to do. And wait, can I try this already? Yeah, I can. You can see it is trying hard to distinguish the recorder. It's maybe it didn't learn anything. I just scaled it down. And you can see it's having a hard time distinguishing between these two pretty similar sounds, like they're both kind of wind instruments. It seems to make slight progress, but really not that much. Not much is happening. And, you know, again, what if we just break this short and say, hey, what if I just expand this and I add, you know, another layer of 10 here and try this. And now actually let's try something. What if I render like now I've got a new neural model. Let's actually look at this. Let's render this neural model. Oh wait, I need to get the model of the AI. Oh gosh, I don't know my own. So I can get the model of the AI. The model is the list of its weights. And I can render that. So I can see this is how my neural network looks now. And I can, maybe this is a little bit too thick. Let's render it a little easier like this. And, you know, let's actually do this and always look at how it learns. And let's find out. Oh, wait, this is wrong. It needs to do. Let's do this. Now we see both. And we can see it's actually learning. The same thing. First, we've got data without needing to introduce XOR or any mathematical stuff. It just can't distinguish between a harmonica or a recorder. But now it can. And it's taking a while. And sometimes it helps if it doesn't render so much. So I can take the neural model out, then it's a little faster. I can also take this out and leave it a little while. The point here is we want to work with data that connects to the learner, that connects to us, not just dead stuff that has been cooked up or carefully compiled for this particular purpose to teach you this one thing, but experience it with stuff ourselves. Let's find out how well we're doing here. Not bad. So we can actually pause this. And here's another thing where we can say, we can not just train a model, we can also validate it. We can see now we're actually using it on the data and see how well it does. Oh, it's 96% from that training data. That is actually good enough for what I'm going to try now, because I now want it to tell me, I now want to do something else. I want to get the microphone, not the microphone volume, but I want to get the samples from my microphone. And I'm going to get the first 100 samples of that. And I want to classify those samples, right? I want to classify those samples with that network, with that AI thing I've done. And I want to do this until the volume is less than a threshold, then I want to switch to the costume of that. I'm going to do this a couple of times to increase the precision. Okay. Does that work? Let me try. It might not work. Switch to the costume. Turtle. And do this forever. Let me first try what I'm getting out of here. What am I getting out of here? 2. Yeah, this looks great. Okay. So this is something where we can bring data from ourselves and do something about it. So this was the state last week. So you can have as many neural networks as you like. You can have ad hoc neural networks. You can now take this, what you've trained, you can get the model of this neural network. The model of this neural network is just a list of lists of the weights. You can export this and share it with your friends. They can import it and assign it to a new neural network and use it to classify their instruments. Or they can retrain it, or they can post-train it. They can do all of this. And I thought this was pretty darn cool because now we've sort of got them where I want neural networks to be. Just a resource, just a bunch of blocks we can use for funky stuff. And I've spent weeks going through all the data sets, and I can share all the resources about the data sets, having tremendous amounts of fun by predicting everything from wine quality to diabetes. And then we thought, well, there's one more thing I'd like to try. And Yatka and I sat together because Yatka was adamant that it should be able to distinguish something else. Like it should be able to also distinguish things like handwriting and gestures. Remember, Yatka and I a while ago did the grand gestures activity for gesture detection. So I decided, what if we try this with the grand gestures, but instead of the $1 gesture recognizer algorithm, we use a neural network. And in doing so, learn something else about neural networks, how we can maybe make them disappear altogether. Okay, enough. So let's make a list. What I want to distinguish is, I want to distinguish a heart from a house from a star. Remember, that was kind of the activity. So what I've got here is, I've got a block that lets me scribble something. So I can scribble something like this. And what I get is a list of not points, but a list of directions. So this is always the direction to the next point. And then it's sort of like a vector, right? So what I could do is I can say, I want to get a list of these scribbles, and I want to mark them. I want to tag them. I want to tag each scribble with its name. And I'm going to set my database of scribbles to that. I'm going to clear. Wait, after that, I'm going to clear. Before that, I want to set the pen size to a little something bigger. So now I need to draw a heart. Let me draw a heart. Actually, let me draw a heart again. Better. I need to draw a house. Gosh. Das ist das Haus von Nikolaus. And I need to draw a star. Star. Okay, good. So now I've got 3 specimens in here. Because another thing that we're worried about is that when we're working with neural networks, you need masses of data for them to do anything right. Like you need to have thousands of specimens of pictures to train them. So I'm just training them with one example for each, and it's tagged like this. Okay, good. Let's try to make it actually learn something. So now what I need is a truth table where I'm saying, okay, I'm again mapping over this list. No, I'm saying for each tag in this list, I want to look at this. No, I need to import the neural networks library. Okay, this is what I'm missing. The neural networks library, the first block in the neural networks library is really provocative. It is generate a predicate. So it doesn't even say anything about neural networks. It makes a block, a predicate that tells you, is this a thing? So for each tag in this list, I want to generate a predicate for that tag, depending on that data. So what I need to do is I need to map over the scribbles and append the first items, like items 1 to 64. Those are the actual things. And if the last item,
is the
excuse me,
goal.
if the last item happens to be the tag, then it's 1, otherwise it's 0. For all,
The number 64.
that's in my scribbles. It's got 64 features.
Okay.
64 columns.
Okay.
They all need to be the same size. So now what I can do is, gosh, I should have practiced this. Now if I run this, what should happen is, see, it's not working. Okay, good. What am I doing wrong? Thank you. It was in the wrong slot. Yes, this looks more like it. Now the heart has, okay, good. Maybe I do need glasses, better glasses. Yeah. Yeah. Okay, so now let's actually run this. So see what's happening is it's now doing all automatically. It's creating a bunch of ad hoc neural networks. It's training them until it thinks it's got them trained enough. And it actually internally normalizes them and sets aside a validation set to test whether it's actually learned not just from the training data. So now what we have is we've got 3 new blocks that it made all by itself. Is it a thing a heart? Is it a house? Or something? If we look at this thing, all of these look like, oh, it's just a bunch of numbers. It makes a new neural network. It sets the model to a list of, the weights that it's determined. And what it also does is underneath here, it also does a min-max normalization, because sometimes the numbers, like if they're far apart, you get all the wrong things. So it does all of this automatically, and it just generates a block that uses this. So now I can make a recognize block. Look at this. I can say recognize. Let's recognize a scribble. Recognize my scribble. So I can say, ha, if the shape is a heart, report heart. Else if the shape is a house, report house. Else if the shape is a star,